Hello, everybody. It's a pleasure to be here one more year presenting a booth talk in the OpenMP booth. This time we have to do it virtually. We cannot meet in person, but hopefully next year we will be able to meet in person again. So today I'm gonna talk about the latest news about our AppEntrust Parallelware tools, in particular Parallelware Analyzer, and one topic that has attracted a lot of attention in the HPC community, that is data race detection for graphical processing units using OpenMP. So this is the title of my presentation, Data Race Detection for GPUs using OpenMP. My name is Manuel Arenaz. I am CEO and co-founder of AppEntrust Solutions, that is a startup company that is developing and releasing products based on the Parallelware static code analysis technology, specializing in parallelism. So what are the major challenges in GPU programming today? Okay, in general, developing bug-free C++, Fortran, or a mixture of these three programming languages, parallel code, is much more complex than developing sequential software. One of the main reasons is that fixing and finding bugs in parallel software, let's call them parallel bugs, is very difficult and time-consuming, because usually what we have is a bug in parallel code appears 99% of the time, and just the code runs correctly 99% of the time and fails just 1% of the time. What this means is that many times it's very difficult for developers to reproduce an error that appears in software that has been released for production. And this is general of parallel software development, and this is even more difficult for GPUs, where we have to offload the computations, offload the data to the GPU, and run the code not in our computer, but in a different device attached to the CPU. So this is even more difficult, and we don't have tools at this moment that are as efficient as tools for finding bugs and fixing bugs in the CPU. So in order to take advantage of the huge performance promised by GPUs, developers need to address two main challenges. Challenge number one, and the more important one, is data movement. What this means is that when you move data from the CPU memory to the GPU memory, you need to guarantee that the correct data is moved from CPU to GPU, that the data that the GPU uses is the correct one. You don't have stale data on the GPU memory that will produce wrong results, and then you transfer back all the results from the GPU memory to the CPU. So you need to keep all the data properly synchronized for your program between the CPU memory and the GPU memory. And this is the more challenging issue that developers need to address. The second one is data races. This is related to parallelism. So when you have a loop, for instance, you need to run it in parallel, in multi-threaded mode. So in general, the same typical problems that you have in multi-threaded execution on a CPU, you have similar problems on the multi-threaded execution on the GPU. So these are the two main challenges, data movement and data races. So how can we help programmers, and in particular GPU programmers? GPU programming is very hard and usually very intrusive for your code, because in order to port a single piece of code, a loop, to the GPU and run efficiently, you need usually to make major changes to your code, not just recoding the loop. You need to recode the data structure, recode the design, reinitialize data, and propagate all of these changes across all your functions, all your classes, all the code, until the point where the target loop that you want to parallelize is executed. So in general, this makes GPU programming much harder and much more intrusive than developing multi-threaded code for CPU, for instance. So which are the major efforts that the GPU programmer needs to address or put focus on? Number one, detection. We need to detect parallel bugs, either data races or data movement issues. Verification. Number two, whenever there is a code that is already parallel, is the developer certain that the code is correct, will run correctly and free of data race and data movement issues? These are different type of development that the programmer needs to do. Discovering opportunities. So you have a piece of code with loops already parallelized, and you want new loops that you want to convert into parallel code and run them, offload them to the GPU. So it's again a third effort for the GPU programmer. And finally, implementation. When you discover an opportunity, you need to implement and code different versions for the GPU and make changes to your code until you find the one that performs better for your code on a target GPU. So in the end, these are 4 tasks that the GPU programmer needs to do, and they need to do it iteratively through the development lifecycle many times since the beginning, when they start to work on a code, until the end and they finish porting that code to the GPU. So clearly, there is agreement in our community that new development tools are needed to improve programmers' productivity in general, and particularly for GPUs, as they promise huge computational power. And they need help in finding and fixing parallel bugs, both data races and data movement issues, and helping also important to prevent parallel bugs. If we can help the developers to write the code in such a manner that they can minimize the probability of a parallel bug appearing, they can save a lot of time and many, many dollars at the end of the day for the company or for the organization they are working for. Okay? So we are collaborating in efforts worldwide in the US and in Europe and with other customers and partners across the world in trying to standardize a process to develop and establish parallel programming best practices. What experts have in their minds, we want to put it in written, write it down so that we can have all that information collected in one single place, accepted by the community and ideally maintained by the community. And also have the possibility to create tools that can automate and many of the tasks that the developer needs to do repeatedly. So from these collaboration efforts, we have come up with 3 stages for the parallelization process. Generic stage 1 is prepare your code for parallelism. Even before starting to code and add any OpenMP programs, for instance, to your code, think about how the code is written, the functions that are created, invoke, the data structures, how the data really laid out in memory, how the data are used by the loop when the code is executing on the CPU. Typical problem that we address here is try to find a data structure that is an array of structs and convert it into plain arrays or structure arrays, because these are data structures that are better prepared for parallelism. So stage number 1, many things that you can do in your code to prepare the code for parallelism. Stage number 2, you already know your code. You have analyzed it and prepared for parallelism, but you have not added any single parallel semantics to OpenMP programs, for instance. So then you need to understand the semantics of the code and what loops can be converted into a parallel equivalent. Typical loops that compute reduction operations. Can we execute the reduction in parallel with the appropriate synchronization to guarantee that the result will be correct, first, and second, that the runtime of the code will be faster? So this is stage number 2. We don't really care about increasing the performance. We want a first version that runs correctly. Many times it slows down the runtime of the original version, but we have a starting point to optimize the parallel code. And this is the goal of stage number 3. So stage number 3 is optimizing your parallel code. And here we can optimize in many different dimensions. Optimize concurrency by reducing synchronization barriers. Remove implicit barriers that are not needed for your code. You can optimize for data locality. Typical exploit row major data accesses in C or column major data accesses in Fortran. Data affinity, load balancing issues with different types of scheduling, static, static one, dynamic, runtime that OpenMP provides. So we can use many different dimensions to optimize the parallel code that we have created. And you can see that there is something that is common to the 3 stages. That is verifying, finding bugs, fixing bugs, verifying that the code is correct. And this is repeated in every single step that you do in every single stage. And you can see this common box in stage 1, verify correctness, stage 2, and stage number 3. So remember, 3 stages: invest time in preparing your code. Stage number 2, invest time in understanding your code and coding a first version without really worrying too much about performance. And stage number 3, care about performance. Okay. So how can we ensure parallel programming best practices? Okay, we need to essentially, the approach is based on 2 pillars. Pillar number 1, let me begin on the right. Open catalog of defects and recommendations. We need to write down all the expertise of experts in a catalog of defects, common errors, explain why these errors are important, when they appear, and how to fix them. And recommendations. How can we write the code in a way that is more amenable for parallelism? How can we detect the situation, and which is the code change that we need to do to prepare the code for parallelism? So this open catalog, you can see we have created an open catalog based on our collaborations with the HPC community, and you can discover many checks, many defects and recommendations that are available there. And also, with this knowledge, you can learn from it and apply it to your code. If you are coding just a simple 200 lines of code application, you can do it by hand. But whenever we go to big codes of millions of lines of code, what really helps in increasing productivity of the developer is to have tools that can check your code against this catalog of defects and recommendations and suggest recommendations to prepare the code and suggest defects or errors that have been found in your code. And this will speed up the development effort. And this is where Parallelware Analyzer tool comes into play. And this whole approach that we have been working on for more than 1 year now has recently received the prestigious Innovation Radar Prize to the Innovation Science category this year. This award was honored to us in September, just 1 month ago. So we are really excited that the community is taking or adopting this approach and is behind it. So what about Parallelware Analyzer? Parallelware Analyzer was first presented as an emerging technology at SC18. 1 year of development has come up with a set of parallel command line tools that can help you both to test and debug parallel code, finding and fixing race conditions and data movement issues, and also help you during the coding process while you have to code different versions of the code. So you have 4 tools in the suite at this moment: PW report, PW check, PW loops, and PW directives. So all of this, the shape of Analyzer, has been developed in conjunction with partners in the PIC and Maestro projects in the European Union. And now recently, at the mid of this year, we have also started a project with the Orange National Laboratory to push data race detection for GPUs using the Parallelware Analyzer approach and the catalog of defects and recommendations. So this is an example output of PW report. What is PW report? Is your friend, is the entry point to analyze a code and to check the status of the code from time to time, because it provides you a summary of code coverage in terms of files, functions, loops that were successfully analyzed, and also a summary of metrics in terms of recommendations, defects, opportunities for parallelization, data races that have been found, and data race-free loops that have been verified by the tool. Okay, and it also suggests new commands of the other tools of the Parallelware Analyzer suite: PW loops, PW directives. Okay, so remember, PW report is your friend. PW check is the tool that is designed to check and find data races and data movement issues in your code. So the help will provide you with the list of defects and recommendations currently supported by the tool. And essentially, we are supporting all the defects and recommendations that are publicly and open, available in the catalog of defects and recommendations. So let me show you in this presentation just a glimpse, 3 examples, 1 example for each of the stages of these best practices recommendations for parallel programming and for GPU. Let's begin with stage number 1, preparation of code for parallelism. And let me bring to your attention one very typical example. One of the major problems of coding code for OpenMP or OpenACC or directive-based standards is handling the data scoping properly. When a variable needs to be privatized, needs to be shared, needs to be reduced, when we need additional synchronization to guarantee correctness. So here you have an example, PWR002, declare scalar variables in the smallest possible scope. And this is just an example of the information available in the catalog where you can see the code before and after the recommendation. And if you see that in this case, you declare this scalar variable t inside the loop, you can even avoid the need to handle the variable t in the clauses of OpenMP. It simplifies the implementation of OpenMP. So if it simplifies the implementation, simplifies the maintenance, and also prevents bugs from appearing, because you may be sharing or privatizing t in a wrong manner in big codes. Okay, so this is one example related to a big, an important topic, that is data scoping. And I want to remark here the nature of the recommendations, the preventive nature. It can help you to prevent parallel bugs from appearing, simplifying the coding, the parallel coding process, which is really important for productivity and results for the developer. An example of stage number 2. In stage number 2, we are worried about creating the first parallel version of our code without caring about performance, but having something that works and works correctly, provides correct numerical results. So in this case, we have selected an important problem that is deep copy. Deep copy, when you go to GPU and you have complex data structures, you need to manually implement in OpenMP how these pointers to structs of pointers to structs to pointers of struct nested structs of pointers are mapped to the GPU. Okay, so here we can detect in analysis through PWD006 missing deep copy of non-contiguous data to the GPU. We can check if what you are transferring in a map clause of OpenMP is contiguous in data or not. If it is not contiguous, then OpenMP by default will not manage data transfer correctly. So you will need to fix it with the mechanisms that OpenMP provides. One way is to provide exact ranges of data that need to be transferred, for instance, in a double pointer, or using best practice recommendations, that is, use enter data and exit data to map all the data and follow the pointers to the GPU. Okay, so again, deep copy, a big problem. We can detect defects in big application codes. And remember, defects are about finding and fixing bugs. We can say, this is the bug that you have, and this is the solution for the bug. We can suggest how to write correct parallel code. And in some cases, even rewrite the code for you. And finally, stage number 3. Now we really care about performance. What dimension do we need to optimize to increase the performance of our parallel code? And in this case, we have brought a best practice recommendation that has been published in IWOMP papers, for instance. That is, when you are on the CPU, you typically are recommended to use parallel 4. But this doesn't map well to the GPU, because in the GPU, you can have different compilers that are mapping work sharing constructs in a different way to the target platform. So for instance, for the GPU, it is best practice recommendation to use not parallel 4, but instead target teams distribute parallel 4 and even additionally SIMD to exploit all the computational power of a GPU. So you delegate on the GPU compiler to create the threads in the appropriate manner so that they exploit all the massive computational power of the GPU. So here we really care about performance. So other examples are collapsing loops or using row major or column major data accesses in C or Fortran. So there are many ways in which we can help you to optimize the performance of your code. And these are just 3 examples of the whole catalog. Here you can see the current status of the catalog as of October. But now we are already working on 5 to 7 more defects and recommendations that will be published before the C. So stay tuned with the catalog, what defects and recommendations apply to, in general, parallel programming, and in particular to GPU programming. And here you have highlighted at this moment the ones that are related to GPU programming, 2 defects, defect number 3, defect number 6. And about the recommendations, there are some of them that are related specifically to OpenMP, but many of them are not about OpenMP or OpenACC or how you implement the parallelism. They are about how you code in C or Fortran. So, for instance, declare global variables as function parameters, or declare the variables in the smallest possible scope, or explicitly declare pure functions are different coding styles for you to write your code in such a way that your code will be better mapped by OpenMP to the target hardware platform. So in the end, you will have a better code, higher quality, less development effort, less maintenance effort. So please watch the catalog and the changes. Feel free to contact us if you are interested in collaborating in populating this catalog with new defects and recommendations and collaborating this HPC community effort. And also we have published, and we will regularly publish tips to avoid, for instance, race conditions for GPUs. You can download it for free from our website, where we describe some of the defects and recommendations that apply to GPU programming. And that's it. So we really hope that you are as excited as we are about this new approach to parallel programming based on these best practice recommendations by experts of our HPC community. And in particular, you can apply this to GPU programming to improve the quality, the performance, and reduce the development effort of your GPU program for the most powerful supercomputers in the world. So feel free to reach out and contact me if you are interested in staying tuned or collaborating with us in any manner. And feel free to open the catalog and download our tools. Thank you. Thank you very much.